Thank you very much, everybody, and thank you for the introduction. I realized after giving the slide set in Japanese to be translated, that is, I realized there wasn't a slide about who I am, so I might as well just quickly introduce myself. So as the nice lady said, I hail from a small company called Technologeeks. It's a difficult name to pronounce in English as well, believe me. It's a poor choice, I guess. And we are essentially consultants and trainers that do all sorts of work around internals. So internals, security, primarily nowadays in the mobile space, and this is what I've basically come to talk to you about. I myself have also written a couple of books, which is maybe some of you have read. macOS iOS internals is the first one, which is now coming in a second edition, as well as Android internals. And what I'm talking about now is actually something that is covered to an extent in the books, because it's basically an implementation that works across all mobile devices that are based on the ARM platform. And of course, nowadays, everything mobile is in fact ARM. Now, how are we going to tackle this, and what are we going to talk about? So we're going to start off with an explanation of the basic concepts of what is known as the TrustZone architecture. In order to do that, I am going to have to involve a little bit of low-level processor stuff and to introduce what is essentially the ARM version 7 and the ARM version 8 architecture. The ARM version 7 is the actually still more popular of the two, although that is the 32-bit architecture. And then we have the ARM version 8, which is where the world is heading towards a full 64-bit architecture. TrustZone was originally devised for version 7, but has been incorporated fully from the ground up as of version 8 as well. Now, we're going to then talk about the actual implementations, because TrustZone, as you will see, is just a specification. It is just essentially a trusted computing platform, just like Intel has. And it is up to the implementer of the software, in particular the operating system, in order to define what they want to do with it. And so naturally, again, in the ARM space, we have really just two operating systems to consider, unless there's some Windows Phone users here, and I don't see any of those, so we're fine. And so we've got the iOS implementation, what is unofficially or internally called Watchtower by Apple, more commonly known as KPP, the Kernel Patch Protector. And then we've got the Android implementations, and notice I'm saying implementations in the plural, because Android is a very open and wide operating system that Google just basically lays the foundations for, but every vendor is pretty much left to their own devices as to the exact implementations, which flavors or which specific drivers and which hardware they implement it on. And because TrustZone is a hardware-dependent feature, then also the implementations will in fact vary. But that's generally what we're going to talk about. So to begin, let's talk about the basic idea, which is what we call TrustZone. And in the ARM64, I'm also going to introduce something called ELX, which are exception levels, where X here is just a placeholder for a number that may be 0, 1, 2, or 3. So what is TrustZone? As I said, it's essentially a platform for secure computing. It is what we call a secure execution, a trusted execution environment. You're going to have to excuse the kanji. It's not actually kanji, it's Hanzi. It's, I delivered this in China, and so I went to the great length of translating this, and I realized it's probably around the same idea, but it might be a little bit wrong, so please ignore that. But anyway, the idea is that we have the basically what we call the secure world. Antoine Shiji here, or the non-secure world, where the idea is that the operating system that we would normally use, and that would be, in our case, iOS or Android, would run in the non-secure world, in a place that is not trusted, which is essentially the same execution environment as you know from any other architecture, like from Intel as well. However, there is also an additional execution environment, which is called the secure world. And that secure world is essentially something that has full isolation from the non-secure world. So we're basically thinking in terms of virtualization as if we have a virtualized environment, but in practice, it's the exact same processor and the exact same MMU. However, we do have a separation at the MMU level, meaning that through some magic, which I will demonstrate, the non-secure world cannot access the secure world memory. It essentially boils down to a single flag, to a single bit. Now, as I mentioned, ARM has moved to a version 8, which is what we informally also call AArch64. for the 64-bit versions. And because they redesigned the entire instruction set, and because they redesigned the entire chipset, the actual basic infrastructure of the chip, they could afford to integrate TrustZone, not like they did in 32-bit as an add-on, effectively, but rather from the ground up. And this is where they integrated it into a model called exception levels, which we will see in a little bit as we go along here. Now, the important thing to emphasize is that if you are implementing any type of operating system on any type of ARM chipset, this is effectively your de facto standard. There's no real other way to deal with the security challenges facing today. And what are these security challenges? So think about the classic model. In the classic model, we have the rings that you may be familiar with. And when I say here rings, I'm talking about what is also known as the Bell-LaPadula model. And most people are more familiar with the Intel rings, which are ring 0 and ring 3, which provide the ring 3 for the so-called user mode and for essentially like for your operating system that's for unprivileged applications, and ring 0 from the kernel. ARM takes it a little bit differently. We still have the regular user mode. Underneath that, we have what we call the privileged, which is something that is not really from ARM. It's more of a Unix idea, where we have the root privileges versus the non-root. This is not something that the processor would know anything about, but logically it is still another level. But then we see what the processor does see, and that is what we call kernel mode. And again, if this were Intel, this is what I would call ring 0. In ARM, I would generally call this SVC, which is a supervisor call instruction that allows us to move from the user mode onto the supervisor mode, which effectively gives us the full set of instructions of the processor. And this is something that, again, like Intel, the CPU will refuse certain instructions, primarily those that deal with low-level hardware registers, unless you are in this mode. And the only way to get to this mode is through the SVC instruction. Now, normally, in classic architectures, below this, we would just have the hardware. And at the point where we're at the hardware, all security breaks down. Because we're talking about very sophisticated attacks. We're looking at stuff like JTAG. We're looking at stuff like direct reading of the memory through side channels, which generally we can assume that the trust boundary would altogether break at that point. However, in most architectures, if you're in kernel mode, once you've compromised the kernel, you've effectively destroyed the entire security of the operating system. Because kernel mode is effectively responsible for everything that is a security feature. And this was discussed by some of the previous lectures, as you saw. Kernel mode is responsible for the process isolation. Kernel mode is responsible for memory management. If you can run code in kernel, up until very recently, this was the trust boundary. And for all things considered, you could have said that the security of the entire system has been compromised. However, not so in ARM, where we have another layer here, and that is the layer that is TrustZone. The idea is that we have an additional security boundary between the kernel and the hardware. And that gets us to a point that is not entirely intuitive. It means that even in a system that has a rootkit, even in a system wherein the kernel is entirely compromised, you can still access some of those features from hardware and deem them reasonably secure. Now again, I say here reasonably because there is no such thing as perfect security, but it is definitely better than just being able to infect kernel memory, read all the kernel memory, dump all the kernel memory, and thereby get access to basically all your encryption keys and whatnot. When we use TrustZone, some of this memory is inaccessible even to the kernel itself, and that apparently makes all the difference. Now, in particular, how does ARM present it? So if you go to the ARM documents, you'll see that they talk about the so-called normal world. And there we have the processors. And in certain types of processors, which originally were the Cortex-A, which are the ARM v7, they also allowed this new secure world. And as you can see, it's effectively a parallel of the non-secure world. It runs effectively the same things, but notice that there is isolation between the two. And that isolation, as I said before, is something that is done at the MMU level. So just like applications in user mode cannot actually read other processes' memory because they do not have the correct page tables, over here is the same idea. The page tables that are in the secure world are not the same as the page tables in the non-secure world, and therefore we are virtually guaranteed physical isolation. And if there's one concept that you can take away from this entire long lecture, it is that just the idea that we have this physical memory separation. Now in practice, what do we do with this physical memory separation? So yes, it's isolated, but what can we actually put it to good use in? And it turns out there's a lot of uses for it, and those vary by operating system. So in the case of Android, we see TrustZone using, basically the usage is extensive all over. And that is because Android by itself, when Google provides Android, they don't really care too much about security. They have very little control over the hardware. They basically just throw the operating system out there and leave most of the customization and most of the adaptation to the specific hardware requirements on the vendor itself. And so vendors take this in all sorts of ways, and eventually this also goes into the mainline Android. For example, Android N, Nougat, has some of these supported basically intrinsically, as we'll see a little bit later. But what are those uses? Primarily, we're looking at cryptographic keys. And again, think about it from the perspective of threat modeling your mobile device. The most important thing on your mobile device is not for an attacker to get root. Getting root on a server that has a lot of users and a lot of data is one thing, but getting root on a simple, pathetic little mobile device that you got for, something like 5,000 yen, that's not really the big thrill. The big thrill is getting to the information. And so what we do is we take all that information that is essentially going to be encrypted in some way, but then that leaves us the question of where do we put the keys? And that's exactly where TrustZone comes in very, very handy. Not only can we put the keys in a secure element, which you can see here is accessible only through TrustZone, but also we can add logic, and we can actually have a full-fledged driver and an operating system of sorts in the TrustZone element so that we cannot access these keys without some type of software logic and software verification. And so that's the primary use. And Android has basically two mechanisms. One is called the key store. The key store, as its name implies, stores all your keys. And then we have the gatekeeper, which is something introduced in Marshmallow. And this is something that effectively enables you to get cryptographic tokens for passwords. And what's the better use of that than just having everything in kernel memory? Well, two uses. First of all, in kernel memory, if anybody had compromised the kernel, they'd get access to your keys. No longer so. But the other thing is that now, access to your keys, access to your passwords and whatnot, has to go through the TrustZone in order to get a decryption key for that data. And that decryption key can only be gotten if you do the password verification or so. And all of this code is in TrustZone where the kernel cannot actually touch or interact with that code unless there's a very simple channel of message passing. In other words, that code can enforce security checks, and that code, for example, can make sure that if you've tried to decrypt your password more than 5 to 10 times, they can efface the password from the secure element, and thereby effectively remove the key and make the data entirely unreadable. But that's only one of the things you have. You also have DRM, which could be considered as a special case, because DRM is the case where we have digital rights management. We have some stream, and that stream is encrypted with a key. Obviously, if somebody has rooted their device, they would be able to access the key, but not if that key is somehow funneled into TrustZone. We also have hardware-backed entropy, and this is what we call a PRNG, a pseudo-random number generator. So if we want the random number generator to have a secret state, from which we deduce the next keys in the sequence, we cannot risk having this in kernel mode because, once again, the kernel could be compromised. Very big in Android is also the notion of Android Pay, which surprisingly does the same thing as Apple Pay does. And so the same idea here, where you want to store all these specific credit cards and whatnot, you actually put them on the disk wherever you want, but the key to decrypt them is going to be through TrustZone. And last but not least, we have more advanced uses, which is something that we see only in Samsung's case, which is to enforce kernel and boot chain integrity. So what are the Samsung cases, and what are they a little bit different? Samsung, in their higher-end devices, those that are primarily based on Exynos, not those of Qualcomm, are basically with a mechanism called TIMA, which is Trusted Integrity Measurement Attestation. It's actually a made-up acronym that I don't think makes too much sense in English either. But the long story short of this is that it is a facility or a little mechanism that they put into the TrustZone, into the so-called TrustZone OS. And they make sure to not only do the standard uses, but also to check back on the non-secure world. And what do they check back on? When a client requests a certificate, they actually store the private keys corresponding to the certificate in their secure world. And they also make forays or sojourns from the secure world to the non-secure world in order to do periodic checks on the kernel state, as well as what they call real-time kernel protection. And you can think of it from the perspective of exploitation. Any exploitation that requires a full compromise of the system, requires running code in the kernel, usually will also require patching the kernel. Because if you patch the kernel, you can disable security checks, you can introduce your rootkit, you can do a lot of really, really good and cool stuff. So what Samsung claims to say is that they can effectively detect these kernel patches. And this is exactly the same thing, by the way, that iOS does. Now, iOS in 32-bit, we don't see too much use of TrustZone. And I say we don't see because we analyze the kernel, we effectively disassemble and reverse engineer, and we do not see any references to that. But then, in 64-bit, we see quite a few. And that's the whole notion of what I mentioned before is KPP, the Kernel Patch Protection. And this is something that was introduced in iOS 9. It was introduced on 64-bit devices, so for the longest time, people didn't even realize where is it implemented. Because the problem of code running in TrustZone, or in the higher exception levels in ARM64, is that there is no real way to extract it or to see it, because it is that well isolated. And so for the longest time, people believed it is running in the secure enclave, which is what we call SEP, that extra processor that is responsible for Touch ID. Now, this was at the time a logical assumption, but it actually makes more sense to do it in TrustZone on the same processor rather than doing it on a coprocessor. Now, that's not to say you don't use a coprocessor for many things, but for the most part, that part of KPP is handled exclusively in TrustZone. And how we know this is because Apple in iOS 10 decided for whatever reason to actually just provide us with that binary. And that binary is part of the kernel cache, and we'll see that in a little bit. Now, when we look at the implementation, so this is back to the ARM spec. The ARM spec in ARCH32, which is the original ARM v7, spoke of a special register, which is called the Secure Configuration Register, or SCR. Now, this register, like many other special registers in ARM, is flags. So essentially what you see here are little bits, and if a bit is 1, if a bit is 0, that changes some type of feature. It all boils down to one little flag, which is called NS, which is, in other words, not secure. Now, if not secure is 1, then you are not secure, right? But if not secure is 0, then you are not secure, which means you are secure. It's kind of like a double negative here. The SCR can actually be accessed by coprocessor instructions, but again, there's one very important thing, which is it cannot be set from the non-secure world. If you're in the secure world, you can actually access it, read and write to it. And writing to that bit, changing it from 0 to 1, is effectively something that drops you into the non-secure world. But you cannot change it from 1 to 0. The only way to do that is if you actually enter the secure world in very, very specific circumstances, which we will see. Okay, and one of those circumstances is what you see here is the SMC instruction. The SMC is Secure Monitor Call, and it runs the same way as SVC. And again, the MMU is going to do most of the enforcement here to make sure that it will respect and honor that NS bit. And according to that bit, it will also be able to tell you if you can access a particular memory page or if you cannot access a particular memory page. Now, all of this wouldn't be complete if the transition to the secure world could not be something that was left unpredictable. And this unpredictability comes in the form of interrupts. Because if the only way to transition to the secure world would be through an instruction, then essentially I would be able to theoretically patch the kernel, remove that instruction, thereby removing the secure world transitions, and therefore never actually having to run any of that trusted code and reducing the problem to an entirely non-secure one. However, we also have the secure operating system hook interrupts. And interrupts, not only are they unpredictable, but interrupts cannot then be accessed by the non-secure world, which means that when that interrupt occurs, we are guaranteed to get some type of control back into the secure world, where ostensibly the secure code will run and we'll be able to check our system status, detect modifications, and do whatnot. Now, how does it actually work? We have a vector. And the concept of a vector here is something that ARM uses a lot. We call it the exception vector. And if you're familiar a little bit with ARM32, this is very, very similar to the so-called exception vector that ARM32 processors would use for their reset vector and so forth. The position that you see here as SMC is what the exception vector would have normally had as SVC. Only now, instead of going to supervisor mode, we're going to the secure monitor world. And you can also see that we can trigger transitions based on prefetch abort or data abort, which are two types of very common exceptions, as well as IRQ, which is an interrupt request, and FIC, or fast interrupt request. And normally what most vendors would do is they would just classify some IRQs as secure and some IRQs as non-secure. And the best way to do that is just classify the secure ones as FIC and the non-secure ones have them as a regular IRQ going to the basic kernel as before. Now in practice, the SMC instruction is very easy to detect. You disassemble it, it's a well-known instruction. Here I'm mostly focusing on ARM64, although it does exist as well in ARM32. You can see that it has fixed opcode, which is D40, followed by an immediate argument here, which is a 16-bit, and that is left entirely up to the vendor to decide what they want. This is essentially an argument that will be passed onto the secure world, and the secure world can, could be some code checking that argument and doing something accordingly. In practice, most vendors leave that as 0, and iOS, Apple that is, leaves that as number 17 for whatever reason. Now, if you're looking at the actual ARM64, so as I said, this is something that integrates extremely well with the ARM64 exception handling process. And how does that work? So in ARM64, we don't have just the user mode and the kernel mode. We actually have 4 levels, and they call them exception levels, or EL. EL0 is what you would normally call just user mode. EL1 is the kernel. EL2 is reserved, but this is where you'd put hypervisor. So think about it, again, from the Intel perspective. This would be like the Intel VT extensions and ring -1, which is the ring that you would do for hardware-assisted virtualization. In practice, nobody uses that, which is actually a shame, because hypervisor actually allows you to run 2 instances of 2 different operating systems on the exact same platform, on the exact same ARM chipset. So theoretically, you could run 2 versions of Android side by side, or in a perfect world, Android and iOS, and a hypervisor would be able to flip between them. But that's unused. What is used is that there is a level below the hypervisor, and that is what we call the secure monitor. And the secure monitor runs our trusted OS over here. So it's very similar to the 32-bit case, because if you think back, that's basically the same diagram they had in 32, but with the exception that in ARM64, we have the hypervisor support, which enables us more than 1 operating system, which is actually a wonderful feature that we can expect to see in the foreseeable future, maybe in the next couple of years, people starting to actually adopt. Now, the transition into kernel is still the same SVC. The transition to the secure world is going to be an SMC. And the transition to the hypervisor, if anybody ever uses that, is going to be an HVC, which is a hypervisor call. Now notice one important thing, which is that even though the hypervisor can issue a secure monitor, and the kernel, which is supervisor call here, can issue a secure monitor call as well, user mode is unable to access the secure world. And that's intentional. Because otherwise, we would have an attack surface that would be too hard to protect. However, if you are going to attack TrustZone, you have to first somehow either compromise the kernel or go through some faulty driver that would allow you to access TrustZone, and we'll see that in a little bit. If for some reason you want to exit voluntarily, of course, then you would do an ERET instruction, which is the same as RET to return to your caller, but ERET actually drops also to the lower level and its accompanying registers. So this separation is not something you can do just in the MMU. You actually need different registers. And so the CPU in ARM maintains an actual entire set of special registers, of which this is only a partial list, but you can see here that they're all SCR underscore or ESR underscore ELX. The X stands again for 0, 1, 2, and 3, as per the illustration over here. And this actually enables us to maintain a separate state for every exception level. And that means that effectively those are entirely different states that the processor can exist in, where of course we have the ability to just translate or move between transition, from one state to another by the methods I've discussed earlier. Specifically, the most important thing is, of course, that we have a different SP, which is a different stack, which enables us to effectively have a different thread context. But then you can see a lot of other things, including the vector-based address register, including the exception syndrome register, the secure configuration register. And the interesting thing about those registers is that they control processor behavior. So what you could do, for example, is you can then say that somebody in a lower level is not allowed to use the floating point registers. Or if they're trying to use the floating point registers, you need to be notified of this. And we'll see that in a little bit. So overall, that's the basic theory. And setting up TrustZone is pretty easy because the CPU boots automatically into the secure world. So think about back again to Intel. Until now, until our 30-something years later, your processor still boots in like real mode. And then it goes into protected mode, right? So here we actually do it a little bit differently. We first start in the secure mode, and then we drop to the non-secure mode. So in 32-bit, we boot into it, ns equals 0. We set up our monitor vector. The monitor vector is that vector which I've specified over here. So you can specify your own predefined addresses to jump to. And that effectively mandates that from now on, in the non-secure world, an SMC instruction will automatically end up in whatever address you place. So again, very, very similar in design to what the SVC instruction does and what a syscall instruction does in Intel. You have some predefined register. In Intel, it's like MSR, like CSIP and so forth. And these are the same concepts, but of course on a different architecture. In 64-bit, same idea, but we now have to consider 4 exception levels. So we boot into EL3, we set up the vector for EL3, we set up also the instruction that we would go to on an SMC, and then following that we can just drop, where we drop to either EL1 or EL2. In practice, EL1 because nobody uses hypervisor, so we drop directly to the kernel mode. Now, how is that vector going to look like? So in 64, our vector is a lot more complicated than in 32. And if you look at the 32-bit example just again, you'll see that it's a very simple vector. And even though I didn't fill in all the hex offsets, all of these bars are essentially 4 bytes. Now, how much can you do in 4 bytes? In an ARM instruction, not much. Usually branch to some other location. In a 64-bit case, however, you don't have 4 bytes. You have 128 bytes, which of course means you've got a whole lot more. And those are for every single type of exceptions that you have. So synchronous exception, IRQ or VIRQ, FIC or VFIC, and S error, which is a type of other synchronous error that you get. And all of these are essentially 80 bytes. So, sorry, all of these are 128 bytes, which is 80 hex. And altogether, we have here 200 hex. Now, as you can see, the vector is actually made up of 2 levels. The first is the level that you see in color. The second is the level that is based on how you got to that exception. So did we get to it from a lower architectural exception, from a lower EL, which is what you would see here, or do we get from the current EL? And again, it is up to the vendor to decide what to do and how to implement that, which you will see. Now, taking as an example, which is far more concrete, taking the iOS case. In iOS, we don't see all of this. We see only a figment or a fraction of all these vectors because iOS, they don't really care about the full set of exceptions. What they do is they actually put hooks only on 2 types of exceptions that you see here. And actually, I could show you this for real, where if I go to where I have KPP, the nice thing about KPP is that it is, like I said, something that we did not know anything about until one day Apple decided, again, for whatever reason, either a leak or either intentionally to open it up. And when you open it up, it basically is just a simple Mach-O object. Mach-O, for those of you unfamiliar with Apple and with macOS and iOS, is the default format. Mach-O to Darwin is like PE to Windows, it's like ELF to Linux, same idea. So I do JTool, which is my own little disassembler that I use a lot, and KPP, and you can see that it's effectively a small Mach-O binary, which I should just adjust the font. It's just a little bit too big.
Okay, and there you can see that there's a particular source version here, but then there's a particular entry point. The source version actually helps us see which version of source they compiled, and presently iOS 10 uses 275. The original iOS 10 betas actually had, by mistake apparently, the KPP from version 9. Now, as you can see over here, we have the entry point, which is this. And from that point on, we just basically jump into the text segment. So looking at that, we can do a jtool -d. And what I have here, instead of just doing the disassembly that's going to be a little bit too messy, what I also have is a little feature which is a companion file, where I've symbolicated most of this, so it'll be easier to demonstrate. So I'm just going to set it up so I can access this file. And I'm going to do a little pipe more here so we can see it. And the main thing, of course, I want to demonstrate is the vector. So the vector is somewhere here. There it is. Now, as you can see, in the vector, areas where they don't really care about the particular exception, they just do as a halt. And a halt is not a real ARM instruction. It's just a branch to the same address. And why would they do a halt? Because that effectively freezes the CPU. But then, ostensibly during their development or whatever, they can go in through JTAG and they can see how they got there. But otherwise, this effectively, when you see a halt instruction, that basically freezes the entire CPU. And that basically means that there was some unrecoverable error in this case. Now you can see that because we've got 80 hex bytes here, a lot of this after the halt is nop, 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 and only at about 3080 we have the next one and the next one after. I could actually make this a little bit easier to see if I use a feature which is nop suppression, because there's just so many nops here that I don't want the nops around. And again, I'll look at the vector, and now you'll see that all these nasty nops are suppressed, and you can see 80, 100, 180, 200, and so forth. Now I remind you, this is hex. So this 80 is 128, and this, what you can see here, the 100 is 128 times 4, which is effectively, 128, times 2, which is effectively 256. Now, the first entry here, as you can see, EL vector plus 400. Looking back at the illustration here, you can see that's a synchronous, and then there's another one for RQ. For synchronous, notice they're taking the state of all the registers, and then they jump to some handler. The handler is going to do something, which we'll see in a second, and then following that, they just restore the registers, which is what you see over here. STP, LDP are inverse instructions to one another. And then following that, we've got an ERET, which is effectively drop back to whichever level we came from. For the FIC, we have a very simple case where they take the current context, and they just propagate it back to a lower context. So you can see what they're doing is doing a little check on CPACR, which we'll see in a second. That's required for floating point processing in ARM. And then they just basically propagate everything back into the EL1 case by putting in an ERET, which of course jumps back. Now, if you look at the actual flow inside that handler, I can actually show you this at the disassembly level. If I go to handle synchronous, which is over here, it's actually behind me, I think. No, there it is. So you can see that there are some labels, and according to how we got here, we can ask ourselves, was it voluntary? Was it non-voluntary? And it turns out that in Apple's case, there's two main ways of getting there. The way that's voluntary is actually somewhere here below, which is where it says check SMC access. So SMC is if we got there because the kernel asked us to get there. However, there's also cases where we check for CPACR EL1 access, and CPACR EL1 is what effectively controls floating point. So if you want to do any type of floating point instructions, you have to go through this register. And in EL3, they trap access to that register in EL1. In other words, whenever there's some type of floating point operation, you get this non-voluntary transition. And we basically see that's the only thing they do, because in the interrupt case, if I look back at the vector, you'll see that the interrupt case actually doesn't do much. I mean, it does check the CP ACR EL1, but it doesn't call any code here. In other words, whatever code is actually loaded into the KPP has to come from either an SMC or from type of floating point operation that they did. Now, going back to here, you'll see that there's basically three cases. The first is the ACR EL1 access. I should point out that originally, when I was initially starting my research, I was presenting this at MOSEC in Shanghai, and that's where I mistakenly thought it's TTBR EL1. This is because my disassembler had a bug. It happens when you write your own disassembler and you don't use like Capstone or something much easier. But anyways, the idea is that CPACR is the main one, and then we check if we got there through that. And after that, we check for known SMC codes, which we'll see in a second. And if we got somehow, by some unintended case, we throw an exception. And that exception is this particular code, which is BF575402. Now, the kernel side is actually, again, very, very easy to find, because it's got this SMC instruction. So once again, to give you a simple example, if I were to look at, at a random iOS kernel, so we'll go here, and we'll go to iOS, and we'll go to 10, and I can do a jtool -d on how many versions of GNU I have here, God only knows, 3, 7, 8, 9, N61. The N61 means it's coming from, I think it's N61 is an iPhone 5S, so they're all 64-bit. And then it's a simple matter of doing a grep SMC and letting this thing run, and you'll see that there's SMC17. So SMC17 is their way to transition to kernel mode. And of course, when you have the SMC instruction, you know that this is the voluntary mode or voluntary movement or transition to TrustZone. And it turns out with a little bit of more disassembly, you see that there's two other places where this gets called. This is effectively a function that, for lack of a better name, I named secure monitor. And you can see that there's something inside the kernel bootstrap thread and something a little bit lower, way down in the kernel. And notice that as we call the SMC instruction, because the argument is 17, then we have to pass arguments somehow otherwise, because they're all 17. So what we do is we use the registers. And we can register here 0 through 3, where if you see the W0 means it's a 32-bit register, X0 means it's the same register but in 64-bit mode. And you can pretty much see that they're using two main codes. One is 801, which is 2049. The other is 800, which is 2048. One of them they use for locking down memory. The other they use to protect a certain physical address, which is the address of the ARM exception vector itself. So why do they need to lock down memory? Because some memory in the kernel, after the kernel is initialized and that memory is populated, you want to effectively make it read-only. And the way to do that is to write, to then gather all those pages and inform the KPP, now lock these pages and detect any tampering or any changes with them. It's not as trivial as to just loading everything into R segments, into read-only segments, because this is data that can only be deduced when the kernel initializes, when there is your first initial boot, and therefore only then can we actually perform the lockdown correctly. So there has to be some type of code actually asking the KPP to effectively start locking and start hashing these particular pages. Now, of course, our assumption here is that if an attacker has compromised iOS, they can only do the compromise after this SMC instruction is run. So in this way, you can basically see that it all boils down to the SMC interface and how quickly we can invoke these instructions. If somebody were to get in prior to that, say for example, if somebody got in where we're still at the at the iBoot stage, then they could ostensibly patch the kernel and kick this SMC out. Now, what are the KPP checks that we see? So there's a bunch of codes. We already talked about the 402, which is the unexpected code. The main ones that we see are the 401, and this is the modification of a protected page. So the way it works is that initially, when you go into the main entry point, and that is even before the actual kernel gets executed, we have code that runs and hashes all the R-X pages, which are the read and execute pages. That is to say, the kernel text. We hash them with an algorithm that turns out to be Blake2. And if you haven't heard about this algorithm, that's fine. I haven't heard about it either until I researched it from the disassembly, and I figured out those magic numbers also appear in RFC 7693, which is the boilerplate specification of how Blake2 should happen or should be implemented. Long story short, it's just like SHA-1, only it's better. Okay, so it's effectively modeled a little bit after SHA-256 to be exact, and you've got hash sizes that go all the way up to 32 bytes. Okay, for comparison, SHA-1 is 20 bytes. Okay, so it's effectively compatible with SHA-256. You can also get up to 512, although Apple sticks to 256. And so if they do that hashing initially, then they can check later on when there's some type of floating point access, they can periodically check those pages. And apparently what they're doing, because they have to consider performance, is they're amortizing the check so that they don't immediately detect the change, but rather in a window that usually spans anywhere from the 1 minute to 20 minutes, they detect that change and then they panic your operating system. Again, it would be nice if they could detect that change immediately, but that would imply they would have to do the hash on every single operation, which of course would be like pretty much impossible in terms of performance. Now, there were weaknesses in the past, and they've been patched, which is why I can talk about them. The main one is that there was this challenge of kernel data. And a lot of the security policies in iOS, which is basically the sandbox and the code signing, all are implemented through kernel extensions. So because they're kernel extensions, the kernel extensions need to store data, and that data is in read-write memory. And up until the point where they actually started locking down that read-write memory had pointers. And you would set the pointer to null, and that would disable code signing, as simple as that. And it turns out there are additional faults, and a very noted researcher who's a dear friend and a very talented 20-year-old, his name is Luca Tedesco, and seriously, the man does at 20 what I wouldn't be able to do at 50, and he's like the world's best Apple hacker out there, and he claims to have figured out some pretty serious vulnerabilities altogether, still in the latest version of KPP. In iOS 10, what they did is they completely redesigned the kernel. So as opposed to the basic segmentation that they had here, they are now doing more granular segmentation. And as you can see here, they say text and they say data, but there's also data const. And that data const are those segments that will automatically be protected by KPP as well. And that's the iOS case, where you can see that if you disassemble the KPP, it's pretty obvious that they actually have a little Mach-O reader there, which looks at the segments, understands the names of the segments, and according to that, applies protections and so forth. Now, in the case of iPhone 7, it turns out they might be abandoning this whole thing, and they have their own dedicated memory controller. We know this because the error message that we get is from an AMCC, although nobody knows what the middle C stands for. And the other thing is that we generally see that there's no SMC instructions anymore, which means Apple decided to effectively move this whole thing apparently into a controller. When it comes to Android, so in Android, everything is open, and that's a very good thing because we don't have to guess anything, or we don't have to be thankful to Apple for releasing KPP to us. It's all out there, and some of it is actually open source. So on your Android devices, you can always find either a TZ image or a TOS image, depending on the partition name, depending on, of course, your vendor. By your chipset, it varies. In Qualcomm devices, it's actually called TZ, or for TrustZone, and there's also a TZB, which is the backup. In NVIDIA, where they use 3-letter words for their partitions, 3-letter codes, they have TOS, which is for Trusted Operating System, and Samsung just places it on an entirely different unnamed partition. Now, the idea is that the TrustZone image in 32-bit is just an ELF image. And that's similar to KPP being a Mach-O image. The choice of ELF is only because the kernel loader automatically loads an ELF, which is the kernel itself, so it's easier to just load another ELF binary somewhere. And it's not like a linkable ELF binary. It's only the mapping of the segments that we piggyback on top of the ELF structure. And then the idea is going to be very simple. We're going to have the kernel that's going to have a driver. The driver is going to issue those SMC instructions, and that is going to communicate with the TrustZone operating system, which is a TZ image. Now, of course, this also means that there's got to be some type of user mode adapter. And that's why you have, on most devices, some dedicated daemon. The daemon talks to a device, which is a character device or miscellaneous device. And that device driver talks to a kernel module, because the kernel module is the only one that can do the SMC instruction for you. Okay? Altogether, it would look something like this. You've got the user mode application, which is third party. That goes on to the key store service or the gatekeeper service, these are effectively two daemons that are part of the AOSP, which is why here they're in green. These are abstracted by the HAL, which is a hardware abstraction layer, which Android does not supply for you. Google basically puts an open standard as a set of interfaces, H files, and it is up to the vendor to implement the entry points in the HAL and the interface points that eventually will be able to communicate with a dedicated daemon. In the case of Qualcomm, if you have an Android device, do PS-EF or just PS alone, you'll see that there's a QCCOMD, Qualcomm Secure Execution component. And that calls the kernel, but not really the kernel so much as some type of driver in the kernel, which will in turn do the SMC and go to the TZOS, and hopefully the whole thing will flow back, and basically everybody's happy. Again, looking at it from the partitions. So on a rooted device where you have access to DevBlock, you'll be able to see DevBlock platform depending on your controller, and this will be either the TOS here, or it's going to be in Samsung a totally different partition, or it's going to be in Qualcomm the TZ that you can also see here. So again, depending on your choice of device. Just a brief example of how we'd go and reverse this before my time runs out. So you'll see that I have here, I believe, a TrustZone image or two. Actually, I wasn't planning to do this, but I'll still try to do something on the fly. Yeah, so I'll look at the 6 Edge, which is one of those Samsung devices that doesn't blow up in your face. And then you'll see here that there's a little S-boot bin. And I have, because this is a 64-bit binary, I have a small tool that I call disarm, which is effectively a command line disassembler that I use a lot. And of course, if I run it like this, it's just going to spit out a lot of assembly at you. But if I do grep on SMEC, like so, then you'll see that there's a lot of those SMC instructions. And it's through these SMC instructions that you can reverse engineer the entire implementation. So notice that the tool is smart enough to tell you what the register values are. And because these are all SMC 0 in Samsung's case, you get here this particular code. And then, of course, the question is, okay, but what does this code do? For which you can actually look at the very helpful error messages. And if you look, for example, here for a TZ error message, then you can say it says here, successfully informed TZ of boot mode. Okay, so let's go back a step. And if that's a success, there was a test branch not 0. And here there was a function 3FE2C. That 3FE2C gets this particular code. So going back to 3FE2C, which is apparently called in many places. So let's just go here. You'll see that it's effectively DSB, which is something that synchronizes the caches, ignore that, and an SMC. So it's very easy from that point to figure out exactly what's going on and to reverse engineer the entire implementation. You can do that from the secure world if you have the image. You can do that from the non-secure world, which is what I just demonstrated, and that's basically it. The disarm tool is something that's available. There's a link here. Very simple tool, but understands ARM64 assembly very well, and also is able to track the register values in a very simple form of effectively symbolic execution. Google also has an entirely open source operating system called Trusty, which is based off of Little Kernel, which is a small open source component, not to be confused with the Linux kernel that they use a lot, and this is something that you can download off of this particular link and so forth. Linux kernel supports this effectively as of 3.10. ARM64 support is as of 3.8. So generally, if you have an ARM64 device, your minimum kernel version is going to be 3.10. Your likely kernel versions are either going to be 3.14 or 3.18 on Android, and they all, of course, support TrustZone. One thing, which is probably the last very good reference that I would suggest if you want more information, there is a blog by a guy who has bitspleaseblogspot.com, who actually demonstrates that at the end of the day, TrustZone is only as secure as the software that you put in the TZOS. And in the case of Qualcomm, that's apparently not secure at all. So he basically shows a step-by-step hack, which doesn't have to do with flaws in TrustZone. TrustZone as an architecture is very good, and the physical separation is perfect. However, if there is some type of memory copying that is somehow influenced by the non-secure world, for example, you get some type of SMC call, it has a register. Many people use to pass values from the non-secure to the secure world, they just pass a pointer. And that's, of course, wrong, because then somebody could malform that pointer, cause some type of overflow or other type of exception in the TrustZone environment, thereby gain full control of TrustZone. And this is exactly what he demonstrates here. So that's a very, very interesting read. Overall, that's all I have time for. Vulnerabilities in TrustZone are listed here. There's just so many. Again, these are in the implementation, and we're basically done.